So we're looking for the equation of the line that's passing through the points P and Q. So here we have the point P, here we have the point Q, the line that passes through them. Now, nothing is said about whether we want to specify a particular direction for this line, which is built into the vector and parametric equations. So since it doesn't matter what direction, we will just start by going this way from P to Q, meaning we're going to start by finding us the vector PQ. So the vector PQ would be the 7, negative 12, negative 7. And so the equation could look like this. Our starting point is going to be the vector that goes to point P, which is a negative 3, 5, and 9, plus any multiple of the direction vector, which is the PQ we just found. Now, some instances, that's an okay way of writing our answer. I'll go ahead and write a usual version of this. That would be a negative 3 plus 7t, a 5 minus 12t, and 9 minus 7t. Now, the cool thing about what we just did in this last step is that we can now write the parametric equation, because you can see here is our x, y, and z. So the parametric equation would look like this. We'd have x equals negative 3 plus 7t, y equals 5 minus 12t, and z equals 9 minus 7t. That was easy enough. And finally, the C part is asking for the symmetric equations. If we take the x equals negative 3 plus 7t and solve for the t, that would be x plus 3 divided by 7. If we do the same thing for the y, that would be y minus 5 divided by negative 12. And then for the z, that would be z minus 9 divided by negative 7. Well, the t value in all of those has to be the same. So here is our symmetric equation. X plus 3 over 7 is equal to y minus 5 over negative 12, which is equal to z minus 9 over negative 7. Now, of course, this is not unique, so you could have other answers that are still okay. Now, this is something that we will use quite a lot in the future when we get to doing applications problems involving vectors. And that is, we want to find the parametric equation for the line segment, just the portion of the line between the P and the Q. If we have done, as we've done right here, it's the same thing as what we had earlier. Only the t values, because we have used PQ as our vector, the t values would just go from 0 to 1. So it's just like this, but we're restricting the t to be 0 to 1. So this is just the reverse of what we just did. they give us the equation here for a line and ask us to find a point for that line and the direction vector for that line. That's pretty straightforward if you followed what we just did. Here is a point on the line. So the point is going to be 1, 3, and 5. And here is our direction vector. So the direction vector is going to be 1, 1, and 4. Now we've actually done one like this earlier. What we'll do is, here's the diagram of what we're looking for. We've got this line, and here's the point P on the line, 1, 3, 5. And the origin, we'll label that O, is out here somewhere. So if we take the vector here, we need this side of the right triangle. Now, if you remember, we just did that recently. If this vector is U and the vector on the line, any vector on the line, is V, then we found that that distance, which is the magnitude of U times the sine of theta, can be transformed into the magnitude of U cross V divided by the magnitude of the V. So that's what we need to find. The vector U would be from the point P to the origin, which is going to be the same thing, since the origin is 0, 0, 0, which is going to be the same thing as P. Now technically it would be the opposite, but we will go ahead and put this in the opposite direction, and so for convenience we'll just use, I'll go ahead and write these down, we'll use the vector U as just the 1, 3, 5. Now again, that only works because the other point is the origin. And then, of course, the vector V is the 1, 1, 4 that we've already come up with. So here we need to do the cross product of U and V, do the magnitude of that, then do the magnitude of V, then divide. Now, I'm not going to take the time to do these manually. I will do them on my calculator and just type it in. So the magnitude of U cross V is a 3 root 6. And the magnitude of V by itself is a 3 root 2. And you can see that comes out to be root 6 over 2, which is just a square root of 3. Looking at the equation for line 1, we see that it goes through the point 1, 0, and 2. And it has a direction vector of 1, 1, 1. So the direction vector for line 1 is 1, 1, 1. Line 2 is written in symmetric form. So again, we're going to convert this. The x minus 3 is a t. The y minus 1 is a t, and the z minus 3 is a t. So this makes x equals 3 plus t. This makes y equals 1 plus t. And this is z equals 3 plus t. So this goes through the point 3, 1, 3 and has a direction vector of 1, 1, 1. Since they both have the same direction vectors, they are parallel. Now I'll just explain this a little quicker because it's just like what we just did. Just got to be creative in setting it up. Make sure you draw things off as you go. Here we'll choose line 1. Now the line that's parallel to that is line 2 out here somewhere. However, here we need a point on line 1. Well, we just said that a moment ago. 1, 0, and 2 is a point on line 1. And we need a point on line 2. So a point on line 2 is 3, 1, 3. And again, just like we've already done a couple of times before, we have this vector that we can project onto here. And again, that is this. If we call this vector u, the line 1 vector v, then our answer is going to be the magnitude of u cross v divided by the magnitude of v. Now I'll just set these up. The u vector goes from P1 to P2. P1 up here on line 1 was, what did we say, 1, 0, 2. And on line 2, the point was 3, 1, 3. So then the vector from P1 to P2 would be the vector 2, 1, 1. And then we've already found the vector to be a 1, 1, 1. We'll do the cross product of those two divided by the magnitude of that. And again, I'll go type that on my calculator. That comes out to be a square root of 2 and a square root of 3, which simplifies to the square root of 6 over 3.